Before, when we talked about unusual results or unusual events, we considered an event unusual if it had a probability less than 0.5. So if the probability of the event X is less than 5%, 0.05, then we consider that to be an unusual event. That's the probability approach. Here we're going to use the range rule of thumb approach. And using the range rule of thumb approach depends on understanding that most of your data values lie within 2 standard deviations of the mean. And so we can find the largest usual value by taking the mean and adding 2 standard deviations to that number. And that will give us a number that we call the maximum usual value. And it's 2 standard deviations to the right of the mean. Then we can find the minimum usual value by taking the mean and subtracting 2 standard deviations, and that number will be called the minimum usual value, and that's just 2 standard deviations to the left of the mean. And so what we see is, when we do this, is that our usual values, or values we expect to occur, are data values that are in this interval between within 2 standard deviations of the mean. So any x values that lie within 2 standard deviations of the mean would be usual, or values that we expect to occur. On the other hand, any x values or any data values that we find outside of that interval, and that is any data value that's more than 2 standard deviations to the left or more than 2 standard deviations to the right of the mean, will be considered unusual. So those are going to be unusual values, these guys and these guys. Okay, so that's using the range rule of thumb approach. And it's actually equivalent to the probability approach. And it's equivalent to the probability approach because if you remember this empirical rule, the empirical rule for bell-shaped distributions told us that 95% of our data are within 2 standard deviations of the mean. So if you take your mean, and here it's a sample mean instead of a population mean, if you take your mean and add and subtract 2 standard deviations to that mean, you will find that approximately 95% of your data values will be within those will be within that interval. But that leaves 5% of the data outside, and that's where that 5% in the probability approach comes from. It comes from this empirical rule. Well, that 5% is divided equally between these 2 tails. These are called the tails. Remember that. These are the tails of the distribution in the normal curve. And so the probabilities of those 2 tails are 2.4 plus 0.1. That's 2.5%. And again, that's 2.5%, and that adds up to 5%. So the 2 tails contain about 5% of the data. And so that's where the 5% comes from in the probability approach to unusual values. So you should be able to determine that something is a data value is unusual by using either the probability approach or the range rule of thumb approach. So all you have to remember is that an unusual event is an event that has a probability less than 0.05, and that's what 5% is. And so having x or fewer with a probability of less than or 5%, or having x or greater with a probability of less than 5%. So those are considered unusual events. It's a little confusing if you read this text, but it says essentially the same thing. An unusually high number of successes, X successes among N trials is an unusually high number of successes if the probability of X or more successes is unlikely with probability of 0.05 or less. And this is how you write that. The probability that you have a data value that's equal to X or more is less than or equal to 0.05, which is 5%, and that's going to give you an unusual event. You can also have an unusually low number of successes. If there are X successes among N trials, that will be an unusually low number of successes if the probability of X or fewer successes is unlikely with a probability of 0.05 or less. And again, I want to point out as in this starred statement, that value 0.05 is not absolutely rigid. Other values could be used to distinguish between results that can easily occur by chance and events that are unlikely to occur by chance. But in this part of the text, we're using 0.05. So again, let's recall the probability approach. The probability approach compares the probability of your event to the number 5%, or to the percent, 5%. So suppose you toss a coin 100 times and observe 51 heads. Call this 51 successes. So a success is we observe a head. Now the probability of getting exactly 51 successes is actually a very small number. Getting any specific number of heads has a low probability. But getting 51 heads in 100 tosses is not unusual because the probability of 51 or more heads is actually high. It's actually greater than 5%. So getting 51 heads in 100 tosses is not considered unusual because you're looking at 51 or more heads as your probability. So let's return to the green pea pods example. Again, we have the distribution, the probability distribution for numbers of peas with green pods among 5 offspring peas. So the possible values for x, which is the number of peas with green pods, are 0, 1, 2, 3, 4, and 5. We stop at 5 because we're looking at 5 offspring. So we have to consider that x could be any one of the numbers from 0 to 5. We can calculate those probabilities. They're given to us in this table. We could actually calculate the probabilities in this column. But these are the probabilities for each of those values of x. So the probability that x is equal to 0 is that number. The probability that x is equal to 1 is that number, and so on down the table. So we can find the probability that x is equal to any specific number. Well, what's more interesting is thinking about the probability that x is 1 or less. So here's the probability that we have 1 or fewer green pods. Well, that's not too bad. Since those two events, 1 or fewer, since that event, 1 or fewer, actually boils down to having either 1 or 0, because those are the only numbers that are 1 or fewer. And since these two events, getting 1 green pod and getting 0 green pod, are disjoint, since those events are disjoint, we can find the probability that x equals 1 or x equals 0 by simply adding the probabilities for each of those individual events. And again, this is because those events are disjoint. If they weren't disjoint, you couldn't do this. But since they are disjoint, we can add the two probabilities together. We read those probabilities from the table. The probability of 1 green pod is 0.015. The probability of 0 green pods is 0.001. That gives us a total probability of 0.016, which is less than 0.015. And so we say that that probability is unusually low. There is a small likelihood of observing 1 or fewer peas with green pods. And in fact, this only happens about 16 in 1,000 times, because that's what this number is. It's 16 over 1,000. The expected value of a discrete random variable is calculated by simply taking the x values and multiplying them by their respective probabilities. And so in the previous example, if we wanted to find the mean for the numbers of peas with green pods among 5 offsprings, we would take each x value, and the first x value is 0, multiplied times its probability, which is 0.001. Take the next x value, which is 1, multiplied times its probability, which is 0.015. Take the next x value, 2, multiplied times its probability, which is 0.088. Take the next x value, 3, multiplied times its probability, 0.264. The next x value, 4, multiplied by its probability, 0.396. And the last x value, 5, multiplied by its probability, 0.237. I'll leave this calculation to you, but when you do all of this arithmetic, you're finding the sum of the x times the p of x, and that's what this is, and that's called the expected value. And the expected value is exactly the same as the mean of the probability distribution. It's the same as the mean. expected value is the same as the mean. Okay, so we have this interesting little problem here. Suppose that the estimated jackpot for the Minnesota State Lottery is $50 million. What we want to do is figure out your expected value. Now, the probability of winning the jackpot, you can find that on the website for the Minnesota State Lottery. We could actually calculate that ourselves, but I'll just give it to you as 1 over 175,223,510. It's a very small probability of winning. And it costs you $2 to buy a ticket. The question is, what is your expected value? Okay, so we want to figure out the expected value. It costs $2 to buy a ticket. So to find the expected value, you have to know what the x values are, and you have to know what the probability of each of those x values is. Well, the x values represent the amount of money. So the first amount of money that's interesting is the $2 that it costs you to buy a ticket. Well, that's a negative $2 because you're paying it out. So you're going to lose that $2 if you don't win the jackpot. If you don't win the jackpot, the probability is the rest of the probability out of that number. Well, the rest of the probability out of that number is 175,223,509. So the chances of losing are that number out of 175,223,510. So you have that probability of not winning, and when you don't win, you lose $2. So that's why we have negative 2 for x. But you could win, and if you win, you're going to win $50 million. I'm going to write 50M because I don't have room to write all those zeros there. And what's the probability of winning $50 million? Well, it's only 1 out of 175,223,510. So now that we know each x value and the probability of each x value, we can find the expected value by taking each x value, in this case negative 2, times its probability, which is that number, and add to that the other x value, 50 million, times its probability, which is that number. And we'll do this calculation in our calculator and very carefully enter it. And when you finish that, you should get negative 1.714, which we can round to negative 1.71. That means that in the long run, if we play the lottery lots of times and win sometimes and lose sometimes, we can expect about 1.71, or we can expect to lose about $1.71. Now, really what happens if you win the lottery, you're probably not going to play it another million or 100 million times, so you're probably going to just come out ahead if you win. But if you never win, you're always going to come out behind. Anyway, that's how you figure out the expected value for the Minnesota State Lottery. And by the way, in the long run, you're going to lose money, so I wouldn't advise playing that game. You can figure out this problem if you like. I don't necessarily want to go through this whole problem here. It's just a very similar thing. You're going to pick 3 different numbers, and to win, you have to match all 3 numbers drawn in any order. So I think we can figure this out. So if you're considering this bet, we need a little bit more information in order to work a problem that's dealing with this. So let's suppose that it costs $2 to play this game. So it costs $2. And let's suppose that you can win $1,000. Okay, so let's think about what it means to win. You win if the 3 numbers you picked match the 3 numbers that are drawn in any order. Well, that means that there are actually 6 ways for you to win with your 3 numbers. Let's suppose hypothetically that the numbers you pick are 3, 4, and 5. If you pick those 3 numbers, then any order of those 3 numbers is a winning combination for you. So you would win if the numbers came out as 3, 5, 4, or if they came out as 4, 3, 5, and 4, 5, 3, or if they came out as 5, 3, 4, and 5, 4, 3. So you can see that for whatever set of 3 numbers you pick, you have 6 ways to win. 6 ways to win. Now, each one of these individual events has probability 1 over 1,000, because you can pick the first number 10 ways, you can pick the second number 10 different ways, you can pick the third number 10 different ways. So there's 1,000 different ways to pick your numbers, but there are 6 arrangements that you can use. So your probability of getting a winning combination is actually 6 out of 1,000. All right, well, if you win, you're going to win $1,000, so that's going to be multiplied times 1,000. That's your winnings. But what about losing? If you lose, it's going to cost you $2, so you have a minus 2 times the rest of the probability. What's the rest of the probability? Well, you already counted for 6 out of 1,000, so the rest is 994 out of 1,000. That's the probability that you're not going to win. And so to find the expected value, we add those two together. So I'll let you do that on your own. You can add those two things together and you can figure out what your expected value is. So to summarize, what we learned here is that a random variable has a numerical value associated with each outcome of some random procedure, and a probability distribution has a probability associated with each value of a random variable. A probability distribution has a mean, a variance, and a standard deviation. You should be able to calculate those. The expected value of a random variable is the same as the mean of its probability distribution. And either the range rule of thumb or probabilities can be used to determine whether an outcome is unusual.